All right, good morning, guys. Okay, so page 11. Okay, object moving along a horizontal line has v of t. Want to go ahead and sketch the graph on our calculator. Make sure you're in radian mode. Okay, I like to start off with a 10 by 10, negative 10 by 10 window. So if you do go to zoom 6, at least kind of gets you a quick start as to what the graph could look like. But here it does say that we want the graph to extend from 0 to 11. So you can go to Windows, and we want to extend that x max to 11. And then 0, x min, we don't have to go all the way to negative 10, right? Maybe negative 1, just so we can see around the corner a bit. Trying to make sure I can see all the peaks and valleys of the graph. Okay, good. So if let's say the peaks and valleys got cut off, you can always go back to window. You can always change your y min, y max. Let's say the graph goes too low, and you can't see it. You can adjust your y min to dig down deeper to a lower y value, right? So you're only playing with these 4 values to kind of make sure you can see everything that you need to see in your window. Okay, so let's create a sign line for v of t and a of t. So this is the velocity function. So velocity function, remember, anything above the x-axis is positive velocity, anything below is negative velocity, anything above and anything on the x-axis is going to be your where velocity is 0. So essentially, if you want to sketch the graph here, you don't have to do it, but I want to show you what I'm doing here. This is my velocity function. Anything above the x-axis is positive velocity, anything below is negative velocity. So you start off by looking for my x-intercepts. So if you do second trace 0, this will help you find your x-intercept for you. Second trace 0. So I'm pretty sure that's a 0, 0, but I could just pick a point to the left of my x-intercept, hit enter. Pick a point on the other side of my x-intercept, hit enter. And then now it's going to find that x-intercept for me. Morning. Morning. Okay. Next up, we can find another x-intercept here by doing second trace again, second trace 0. Pick a point to the left of the x-intercept. Pick a point on the other side of the x-intercept, hit enter. This time I get 3. One more time. So just pick a point to the left of the x-intercept, hit enter. scroll over to a point on the other side of the x-intercept and enter. Okay, I get 9. So my velocity sign line could look like this. Velocity starts above the x-axis, so positive velocity. Negative velocity to between 3 and 9. And then positive velocity between 9 and 11. Okay, now acceleration is basically the second derivative graph. So acceleration is going to be 0 at the peaks and valleys, right? Basically, think of it as points of inflections of the how we pull points of inflections off the F prime graph. Look for peaks and valleys. Okay, so if I want to find my relative max, relative min, I go to second trace instead of 0. Now I'm going to find a max. So I'll go to second trace max. Okay, so I'm going to pick a point to the left of my where I think my relative max is. Hit enter. Then scroll over to a point on the other side of your relative max. Hit enter again. And it'll find that relative max for you. Okay, so we care only about the x value here, 1.643. Now we want to find a relative minimum. So do second trace minimum, second trace 3. Okay, pick a point to the left of your relative minimum, hit enter. Pick a point on the other side of your relative minimum, hit enter. 6.542. Okay, so now we look at the slope, right? Positive slope would mean my acceleration is positive. Negative means my acceleration is negative. Positive acceleration. So I have positive, negative, positive. Okay, find the times when the object is motionless. Motionless is when velocity is 0. So at 0, 3, 9. Okay, find the velocity of the object at 4 seconds. So it just simply plug 4 into my velocity function. Y1 is holding my velocity function. So I'm going to go back to my home screen. Alpha trace will allow me to select my Y1 parentheses 4. So I want to find my velocity at 4 seconds. I get -2. Find the acceleration. So acceleration is the derivative of velocity. So I can take advantage of that Math 8 feature, Math 8, and derive. Okay. My velocity function, I'm going to call my velocity function, ask the calculator to do the calculus for us. Second trace, Y1, 4. So -2.314. Okay, is the object's speed increasing or decreasing? We're talking about increasing, decreasing speed. We compare velocity and acceleration. All right, if it's asking about is the object's velocity increasing or decreasing, then we only look at acceleration. But here, increasing, decreasing speed, we look between velocity and acceleration at 4 seconds. I think having everything lined up is nice here because we see, well, also, sorry, we already gathered that information from part C and D, right? They're both negative. We could also pull this from the sign line, actually. Excuse me. Right, we can see between 3 and 9 is negative. Between 1.643 and 6.54 is negative. So at 4, they'll both be the same signs. If they're the same signs, the object speed is increasing. Make sure when you say that they have the same signs that you actually specify what the name of those functions are. If you just say because same signs, that's not clear enough. Make sure you name that you're talking about velocity and acceleration. Okay, find total displacement. Displacement is just definite integral. Total distance involves absolute value. Okay, more interesting. So we'll make the calculator do the work for us here. Set up, show your integral notation, 0 to 11 of v of t. This will give us displacement. Math 9. Okay, it's okay to have displacement to be negative value. That just means that you end up to the left of where you started. Or I said meters here, it should be inches. Find the total distance. Distance, we do definite integral with absolute value. Absolute value only goes around the velocity function, doesn't go around the entire integral notation, just inside your integral between your velocity. On either side of your velocity. Here you can go to math, number, ABS. May take a second here. Okay, next up, find the time when the object reaches minimum velocity. So if we look at our graph here, minimum velocity is where my velocity function is at its lowest. So if I want to find, I found from before, right, that my acceleration sign line, 6.542. So if I just do 6.542, if I do second trace value, I can just give it an x value and it'll find the y value for me. So at time 6.542 seconds, my minimum velocity is going to be negative 6.28 inches per second. You can also find that by doing second trace and going through your minimum feature again. Sorry. All right, so if I want to do minimum again, I can pick a point to the left of my x-intercept, sorry, at left of my relative minimum, hit enter. Then scroll over to a point on the other side of your relative minimum, hit enter. So at no point do you ever want to put your cursor directly at where you think your relative minimum is. Make the calculator find it for you, right? Don't try to do the calculator's job, otherwise they'll get confused. Okay. Given x of 0 equals 3, find x of 11. So I like to use my first theorem rearranged to show particle motion. So if I want to find my position at 11, I can begin at position 0 and then fill in the gaps between how much, in terms of how much progress I made in those 11 seconds. So we start off at location 3. And we already have this, right? We got that from before. So we start off at location 3, but then we travel 10.9 inches to the left. Where are we going to end up? So 11 seconds in, this object will end up on the x-axis at negative 7.993. Average velocity. So that's average value theorem. Okay, so let's find the time when the object actually reaches average velocity, right? We know that if negative 0.99 is really the average velocity, then that means along the path of the graph has to hit average velocity sometime somewhere. What you could do is you can graph negative 0.99 and look for the intersection. Another way that I can think about this is, well, I'm trying to figure out when velocity is equal to this value, right? I want to find the time when that's the same. So what if I do this? What if I do v of t minus this value and set that equal to 0? So now I can just, what if I do this? Now I can just graph this function. And then look for the x-intercept. Right, that's the same thing as graphing the two equations and looking for the intersection. So I'm going to go to y1. I'm going to leave y1 alone. I'm going to call that y1 function by doing alpha trace y1. So now I'm calling that velocity function and I'm adding 0.999. What if I just graph this function instead and then look for the x-intercept? But I don't want all these graphs showing up for me, so I can scroll over to the equal sign, hit enter, so that it doesn't show up on the graph. So when the equal sign is highlighted, that means that graph will show up. So now if I just hit graph, it's going to be a different looking graph, but whenever that graph crosses the x-axis, that is telling me when my velocity function is actually hitting that average velocity. So if I do second trace, I'm going to look for that x-intercept, 0. Pick a point to the left of the x-intercept, hit enter. Pick a point on the other side of the x-intercept, hit enter. Hit enter again, 3.545. Now, if you get that notation, -2.2 e to -13, that just means it's a really small number. That's basically 0. So I don't know why they don't just say 0. It looks confusing, but it's just basically your x-intercept because your y is 0. So 3.545 is a t-value when the object actually hits the average velocity. We can also find the other x-intercept there. So I could trace 0. And we pick a point to the left of the x-intercept, hit enter. Pick a point on the other side of the x-intercept, hit enter. 8.783. Again, that just means it's a really, really small number, basically 0. Yeah. Yeah. No. We got a lot here. Sorry. So do you see a var button on your calculator? Var for variable. Is there a var? I'm like, no.
I am late, but I did from the drive with the wheel being back home. The wheel's the worst part of this. No car, bro. Not the wheel. You got school?
I did wait like 10 minutes for a part of it.
No, because my question's outside. Like I was ready. It'd be 7:05. It'd be 7:05.
Oh, engage var, which is found above the subtraction key. Oh, there it is. Do second var.
10 minutes. That Saturn felt like.
I'll
forget
it. Trace.
Why one?
Yeah. And then parentheses. Oh, okay.
Second
My
var.
gosh. I got you. Yeah, thanks.
Worried about my lab quiz.
Second var.
Yeah, the vote. And there's a line vote.
Arrow down on that menu to find your function y1.
Is there, oh, that's all I have to ask your question.
I think I got Y1.
Was it vocabulary follow how to ask, or was it like?
So it's one.
Yeah, but you want to call that on your graphing line, right? So under y2, do second minus sign. That's what I want for that. Okay, see if that helps. Okay, let's continue. Page 12.
line decision. Page 7 to 15, I understand. Ian, can you go over our photosynthesis and respiration on version five?
That sounds
Yeah.
hard.
What was the control group?
So for which one? Because for one of them, it was all of them.
Yeah, I know.
The other
But
one,
the anything.
but the other one's just room temperature.
The control of whale play.
It's for photosynthesis, the control was all 4 that we tested on the first day.
It could have been the light.
It was all of them.
Anyone.
Oh. But you do like 1A. If we have time at the end, we do that. I want to be like, I can't be away.
Yeah, so 1A, you graph the function. Okay. And then you look for your x-intercepts. Your x-intercepts will tell you where velocity is 0. And then your peaks and valleys will tell you where your acceleration is 0, or where your critical points are for acceleration.
Oh, okay.
For hill and gravity.
Right, so everything is under second trace. So the 0 feature will help you find your x-intercepts. The minimum feature will help you find your relative minimum. And then your maximum will help you find your maximum.
So for all of them, we go like one far to the left and one far to the right, so like find the middle.
Yeah, so you got to do, for every one of them, you got to do them separately. So you can't just hit one button and it'll find everything for you. So for instance, if I want to find this relative minimum, I got to do second trace minimum, and I have to scroll to a point to the left of where I think the relative minimum is. Hit enter. And then it says right bound question marks. And now I'm going to scroll to a point on the other side of your relative minimum. Hit enter again. And now it's going to find that for you. It's going to find that relative minimum for you. Hit enter again. Third time it says guess question mark. And now it's going to find that minimum. So 6.542. So the minimum of your velocity function and the maximum of your velocity function is where your acceleration is 0, because acceleration 0 is where v prime is 0. Right? The slope of your velocity is 0.
Is there a way to like guess too far? Like if you put the bounds too far away?
Yes. So if the graph looks like this, and you want to find this relative minimum, and you pick a point here and pick a point here, it's going to get confused because there's 2 relative minimums, so it's not going to get there. So yeah, you want to pick a point relatively close so that the calculator can actually look for what you want to look for. Some students do this, they put their cursor directly on the relative minimum, both of them, and the calculator gets confused, doesn't know what to do. So make sure you pick points on either side of your target and make the calculator do the work for you.
So there's only gonna be like 2 values on the AT graph, acceleration graph, or
Yeah, because there's only 2 peaks and valleys, right? Imagine if this was asking about points of inflection, right? Points of
Yeah.
inflection on your velocity, on your F prime graph will be just your peaks and valleys.
Alright.
And then the slopes of your F prime graph will be the concavity of your original graph. Okay, so number 12, page 12. Yeah. Mhm.
You can include the answers in.
Answers in the original bounds. You're talking about just carrying it over from above, or? Yes, that's right. That's right. Yeah. So I found 2 answers inside the interval. I found 3.546 and 8.782. Yeah, but you're right. Your average velocity t value is only living between the interval. Anything outside is not part of our answer. Okay, so the graph of f consists of line segments. We have g of x. G of x involves the area between the graph and the x-axis, between the f and the x-axis. Find g prime. So g prime is simply the derivative of this function. So the derivative is just second theorem. Well, if I just write it out as, well, I'm trying to find the derivative of this expression. And that's just second theorem, right? I know the derivative integral notation cancels out, plug the x into the function, I get f of x. So if g prime is f of x, then g double prime is simply taking this and making it go one double down, right? So g double prime is simply f prime. Okay, if it helps, you may want to lightly shade in what you're working with, because there may be other shapes that you see, but only what's between the graph and the x-axis is involved for your problem, right? So it says find g of 4. So g of 4 is just whatever the rule tells us. We're going to accumulate the regions between 2 and 4. Let me go ahead and just label everything I see here. So I see a rectangle, see a square. So from 2 to 4, it's just 1 half plus 1, so 1.5 or 3 halves.
You don't care whether it's decimal or fractions.
As long as it's exact. Like if it's 1/3, I want to see 1/3 rather than 0.333. But if they're exact, then it doesn't matter. All right, g of -2. It's showing going backwards, but I'll make that adjustment after I put it into the rule. Otherwise, if you make the adjustment at the beginning, you may forget to change the sign. So, okay, so now I can see, okay, I prefer to read from left to right. I want to flip the bounds, but if I flip the bounds, I got to make a negative adjustment. So -2 to 2. 1 plus 1 half minus 1 half minus 1 half. Now, so just 1 minus 1 half, so 1 half with a negative outside. Okay, it says find g double prime of -3.5. So g double prime is defined as f prime. F prime is just the slope of this graph. So -3.5 is here. So what is the slope of this line segment? The slope of this line segment is just up 1/1. Slope is +1. Okay, for what value of x is g increasing? So we're asking about g, and in relation to this graph, this graph is my g prime graph, right? This is my g prime. So this is my g prime. I can label accordingly. Pick off my x-intercepts, so -3, 0, and 2. Anything above the x-axis is where my g graph is going to be experiencing positive slope. Anything below is where my g is going to experience negative slope. So negative, positive, negative, positive. Okay, so if I have my slope sign lines, a little bit easier to make my justifications here. My G is increasing in these two intervals, right? From -3 to 0 and from 2 to 4 because G prime is positive. Okay, for what value of X is G prime decreasing? So G prime, this is basically our G prime graph. G prime decreasing is just negative slope, right? So G prime decreasing will be this interval, right? Okay, find the absolute extrema. So absolute extrema, we can pick off our, this is extreme value theorem. We can pick off our critical points and endpoints from our G prime sign line. So we'll have to test all 5 of these points. Oh, sorry. Sorry, only going from -1 to 3. I was not looking at the original interval here. So -1, we go back to our definition here. -1 will be from 2 to -1. With the bounds. So -1 to 2. It's just going to be -1/2. With a negative that's already being pulled out. My other critical point, I'm not going to include -4, -3 because that's too far to the left here. So I'll test -1, I'll test 0, and I'll test 2, and I'll test 3. So from 0 to 2, showing me a -1, but they already pulled out a negative, so 2 negatives make positive. G of 2 is easy because the bounds match. So when the bounds match, I haven't moved at all. So no area to find. That's 0, right? And then from 2 to 3, that's just 1/2. No adjustment with bounds. So we just pick off the highest and lowest y values that we see. We don't care about the x value. The highest y value that we see is 1. The lowest y value that we see is 0.
Why did we skip 1?
All right, so 1 is not a critical point. So if it's not a critical point, then it can't be a max or min. Yeah. Yeah, it's a good question. If there's no g of x defined like this, then we go to that final position equals initial plus displacement. Yeah, so if the problem only says, oh, g of 3 is equal to 6, then if I want to find any point on the graph, that I would use that x of b equals x of a plus. But if a definition, if exact formula is given to you, then you'll use that formula. All right, Riemann sums here. Use trapezoid sum with 6 subintervals to approximate the area of the face of the wave. So we know that our formula will be feet squared, right? This is feet, that's feet as well. So our units will just be, if we're involving anything that's integral or Riemann sum related, we're always multiplying between 2 units. Okay, so trapezoid, make sure you memorize this formula. It's width over 2, height 1 plus height 2. Make sure that even if your trapezoid interval spans across multiple intervals, you're only picking off 2 heights per trapezoid, right? We're not adding up all the heights. We're only involving 2 heights with each trapezoid. Let me change this problem here. Why don't we just make this? Let's do this. Let's do 2 trapezoids, so I can show you that. So 2 trapezoids for this entire interval. So I could just kind of trial and error here. First interval will cover 4 order pairs, and the second interval also 4 order pairs. Make sure that each subinterval spans across the same number of order pairs. They may not have the same width, but it's okay. It's equal number of order pairs. That's important. Right. So the width for my first trapezoid is going to be 24. The width of my second trapezoid is going to be 53 minus 24. $29. So you can say the integral from 0 to 53 of h of x dx can be approximated using 2 trapezoids. So width over 2, so 24 over 2. And we're only picking off 2 heights. We're not going to add up all these heights. We're just going to do 0 and 26. And then width over 2, 29 over 2. 26 plus 0.
It'd not be like negative, because you're going from 26 to 0.
Remember, these are y values. These aren't x values. Right. If it was x values, then maybe that's could be true, right? These are just heights. Okay, estimate using 3 middle rectangles. So 3 middle rectangles. That means I have to span out a different set of. So from 0 to 18 can be 1, 18 to 36 can be 1, and 36 to 53.
Can we change the value to 54 so that they're all 18 on the width?
Hmm?
Can we change the value at the end of 54 so that they're all 18?
The thing we have to kind of get used to is that on the AP exam, you're almost expecting every width to be different. So yeah, but I think it's good practice to just understand that, you know, it's nice if all the width are the same, but chances are you're going to have to do your area 3 separate times. Okay, width of 18, because 18 minus 0 is 18. And then the height is 5. 36 minus 18 is 18. A width of 18, height is 26. And here, width of 17, height of 7. Okay, we're essentially approximating the same region, so it should be, should be in the general ballpark in terms of the values. We're never gonna have to worry about, involving how accurate our approximations are. Just have to be able to find whatever the problem is asking for. Okay, find the average height using part B. So average height, that's average velocity. So 677 is the units here is feet squared. 53 is, that's the width, that's in terms of feet. So feet squared divided by feet. I'm back down to feet, which is average height, which is the units that we expect for average height. Yes. I'm sorry.
That's you to approximate the derivative of the units being.
Yeah, I don't know. This is kind of strange with the units here. But typically, now this is not your normal problem where you can go back and forth. Usually, if they go on, gosh, you got asked you to go back and forth. Usually, time is involved. Yeah. So this one is kind of hard to imagine it being derivative. Okay. We skip page 8. Why don't we look at page 8 here? Okay, so Joanna jogs along a straight path between 0 and 40 minutes. Joanna's velocity is given by differential function v. So interpretive meaning of v prime of 20. So v prime of 20 is involving acceleration, but if we want to use this in terms of using the word rate, we know v prime of 20 is the rate of change of velocity at t equals 20.
What we have to say, like, with the problem, like, it tells us how fast the rate at which she is running is changing at 20 minutes. So just rate of change of velocity.
How did you phrase it?
It tells us how fast the rate at which she is running is changing at 20 minutes.
That's fine. Yeah. Approximate the value of v prime of 18. So approximating basic acceleration here. So for 18, we're forced into using these two order pairs because 18 lands between 12 and 20. So we'll just do change in velocity over change in time. Units will be meters per minute squared. Interpret the meaning of the definite integral from 20 to 40 of v of t. So it helps using first theorem to expand it out to help us see or interpret this a little better, because we know the integral of v of t is position, right? So this is x of 40 minus x of 20. If we think about x of 40 minus x of 20, x of 40 is going to be her position at 40 minutes minus her position at 20 minutes. That's going to be the change in distance or the displacement between the 20 and 40 minutes, right? This is the amount of progress that she makes in those 20 minutes. Okay, approximate the value using trapezoids. So width over 2, height 1 plus height 2. If you get a negative value, keep it. Right. It's okay to have a negative displacement. And then average velocity from 20 to 40, we're using our number from part D, we just do 1 over B minus A. So this is the total accumulation over the 20 minutes divided by our time. So she travel 520 meters to backtracking divided by 20. That means she's making a progress of 26 meters per minute to the left, or back where she was coming from. Okay, I know we did this problem already for on page 7, but are we comfortable with writing out our meaning of if whatever units is given to be able to present our answer in words like these? Okay. So for instance, C of T is ounces per minute. So C prime is how fast the rate of water added to the cup is changing. So we have to use those words. If it's not a particle motion problem, we can't use the word velocity acceleration. We want to be able to use the words that are,
So why do we use velocity in the previous problem?
well, the previous problem was actually like a particle motion. Right. But not 7, right? Not page 7. Right? Isn't page 8 involving velocity acceleration?
Oh, because it's saying, because it uses V of T, or like,
Well, also because right, so it anything involving position, velocity, acceleration is particle motion, right? So you can use acceleration in these, but you can't use acceleration.
velocity in the question.
Huh?
There we go. It says velocity in the
Yeah.
question.
So if it's involving rate at which water is being added, acceleration doesn't fit the context of the problem. So. And also keep in mind that whenever a derivative or integral is involved, your units will always change, right? We can't use ounces per minute anymore if we're involving the integral of that function. Right? Our ounces per minute will turn into ounces, and things like this will tell us if we accumulate the rate of change over time, it's actually going to be the actual amount of coffee in the cup that is changing, right, in units, in ounces. Yeah.
Can you explain like how you use your calculator? It's like find the time swing increases the average velocity.
Yeah. Mm-hmm. So let's go to that previous page. Page 11. So we know that if our average velocity is negative 0.99, we're basically asking when is the velocity going to reach this negative 0.99? We could graph both these functions and look for the intersections, but what if we do this? What if we rearrange this equation and make it v of t plus 0.999 is equal to 0? And what if I graph this equation instead and look for the x-intercept, right? Because that's the same thing. It's also easier to look for rather than have to search all over your graph to look for intersections that may be hard to find. You can just. Yep. So what I did was I took my velocity function, I kept it there, but under y2, I did velocity plus 0.999. And then I unhighlighted my first graph because I didn't want to see that one. I want to see my new graph. And then from here, I'm just going to hit graph. And exactly right. Now I'm going to look for my x-intercept because my x-intercept will be the times that will make this statement true, which is when my velocity is hitting that negative 0.99.
Where are you?
I am subtracting it, but this is, my average velocity is a negative, so. if I
Oh,
subtract the
okay, no,
negative.
yeah, yes.
But yeah, if this was positive, then yes, it would end up being negative. And then from here, you can use second trace. Yeah, you can use second trace value, oh, sorry, 0 to help you find those x-intercepts on the graph. Which ends up being .5 and 8.7. You gotta do it twice. Yeah, I know the calculator doesn't, it can't find all the x-intercepts for you all at once. You gotta do it twice. So if I want to find one x-intercept at a time, I gotta do second trace 0. And I gotta physically go to the left of one x-intercept, hit enter, go to the other side of the x-intercept, hit enter. And that'll find me one of them. And also, if you see a strange number like this, that just basically means 0. That's a really, really small number. So we gotta repeat the process for both these times, yeah.
How did you unhighlight one of the?
Just go to the equal sign and hit enter.
Oh, okay. I'm just not gonna pay attention to
It is part of my.
Yes, I was thinking the same thing.
Buy a second period for me.
I got this, I can do it.
There will be a lot of
Years?
Oh, I know, I can do it.